that without really doing any real mathematics. And we sort of ask what is computationally possible. In some sense, we find that computability is somehow equivalent to provability. So if the spectrum is intersected by a ball, can we prove that that's so the sort of naive approach to finding the spectrum is to do a finite section method. This actually doesn't really work too well. It fails quite catastrophically in almost all cases. Not least because we have a square truncation instead of a rectangular, an adaptive rectangular one. For PDs, we typically truncate the domain and discretize, and we pick a convenient basis and we sort of find some constraints. And so some key issues that come up with spectral pollution. Will be pictured on the next slide, but when we compute these approximations, there might be some extraneous information. There might be some regions that seem like they should have spectra in them, but these disappear as you push it to infinity. And equally, spectral invisibility is where spectral points would not be apparent for approximations. They suddenly just appear. We also have the question of can we compute these spectral properties of error bounds, so we can possibly apply these algorithms to compute just as proof. So just take this example of a second order linear differential operator fix a Hermite basis. The matrix representation of this will be very nice, sparse self-adjoint matrix. However, we get quite catastrophic failure. So the actual spectrum is just these discrete bits here, but we get all of the spectral pollution down here. Obviously, these don't correspond to spectral points, but if we didn't know that the true spectrum was 1, 2, 5, etc., we may indeed guess that the spectrum is just 1 to infinity, which obviously is a problem. It's not even close to the true picture. And an example of spectral visibility is, again, taking the second order linear differential operator, finding the spectrum by just taking the Fourier transform, truncating the domain, applying Dirichlet boundary conditions, and we get this very densely packed but still discrete spectrum. And for the actual operator, we get this nice quadratic curve, but again, from the approximation, it looks nothing like the true spectrum. We almost get the positive half line. And of course, this is again just completely wrong. So quickly, what do I mean by convergence? The answer is just basically Hausdorff metric, or this a two-Gretz metric, which is basically just generalization of Hausdorff metric, essentially. So the role of these terms here is this deals with spectral inclusion. If there are points that are not captured by these approximations, this distance will not go to 0. And equally, for spectral pollution, if there's extraneous points in the approximation, this will not go to 0 either. And essentially, on compact sets, these induced equivalent topologies. This is just an example of what can actually go wrong. We get some kind of numerical instability. The spectrum will depend on the block sizes, and obviously we can't see the block size. If we were just sampling finding main matrix elements, we might we can't determine whether the sequence is bounded, and we get this dichotomy based on whether it is or not. Another example, again, if we want to sample finite many matrix elements, we have this problem of information being hidden away, because if we scan down here, we might see, okay, it's going to be diagonal 0, 1, and we have this information hidden away. So we need to quantify information that we cannot see within finite dimensional approximations. So this is a uniform procedure to find the spectrum. We cannot actually approximate in one limit the resolvent, which is just this inverse norm here, but we can find this doubly indexed approximation, which will converge in successive limits, and we can use this to find the pseudo spectrum. Then we can just take the parameter to infinity to get the actual spectrum. That will give us a uniform procedure in 3 limits. And the question is, can we do better? And the answer is no, because we can embed this this arithmetic problem into the spectral into the problem, finding the spectrum, sort of give a lower bound as to the difficulty of the problem.
What is Arveson's lament?
Oh, at the beginning, he sort of laments about the fact that there was no proven general techniques to find the spectrum. It's quite long. So we sort of form this SCI hierarchy to sort of measure the computational difficulty of these problems. So delta zero solved in finite time, basically not going to happen. I mean, you can add 1 + 1 or something. Delta one, more realistically, is sort of your traditionally computable spectra. And for delta two is just if you might not have error control, and we have delta three and so on. This hierarchy can be very easily generalized to various models of computation. And a kind of example of this is computing polynomial zeros by iterating rational maps. It was determined by McCullum that you can't do this in for degrees higher than 3, and it was later determined that you can do it if you allow this sort of successive limits with iterating rational maps. And this is sort of an early appearance of this idea of successive limits used for approximation like this. So this is just a illustration of what we mean by error control. We sort of, if we have this approximation, then we're sort of theoretically guaranteed that every point in this in this approximation will be 2 to the minus, at most 2 to the minus n close to respect to a genuine spectral point. And pi 1 is sort of very similar. It's sort of every yeah, up to this error parameter, the approximation retains every spectral point. And this is sort of just diagrammatic representation of hierarchy. So we have this the delta 1, delta 0 down here. It's pretty much north of these problems that we have computable. We have these error control classes that are not generally these inclusions don't collapse, and this can basically be understood as a non-collapsing of like the arithmetical hierarchy, which is of which the SCI can be understood as a generalization. So to relate to provability, we sort of want to look at specifically computable output, computable inputs. And we obviously have a choice of computability notion, and what notion we use is going to depend on what we're interested in computing. Sometimes we might find the coefficients of the Taylor series are useful for our purposes. We might want rational point evaluations. We want to compute the matrix elements with respect to some basis. But importantly, it needs to be described by a finite string. For example, pi can be described by a finite string, described as Taylor series. This notion is obviously not going to be intrinsic. You can easily dream up matrices that are computable on one basis, but not in another basis. And the idea is then to embed classical problems in Turing machines that are known to have a certain difficulty. Then the spectral problem will have at least that difficulty, and then you, by realizing that difficulty, you find it. So this is a kind of basic theorem on Schrodinger operators. We sort of we assume that we have a lower bound to the resolvent, and also that we know roughly how the potential varies on each closed integral bound here, and this allows us to compute the matrix elements when we form an infinite matrix based on this operator, and then we can find the spectrum with convergence from below. So we always have this lower bound on the distance, and we grant access to an upper bound. In terms of this function g, which for a self-adjoint we can just take as gx equals x.
What's the operator A?
Oh, sorry, the operator A will just be minus delta plus v, where we sort of just define this on test functions. Then
It's self-adjoint, so the resolvent norm is the distance to the spectrum.
Oh, yeah, we can cut self-joint out, and we can just assume this g, because this g sort of plays the role of self-adjoint, I think that's, yeah. So to build this matrix representation, we sort of form this. We use Debeshi's wavelets. The important thing is, in previous results of this kind, we had to assume decay conditions on V, and we can just get rid of those completely by using a compactly supported basis, and that's easy enough. So the idea of this proof is to just find an upper bound to the distance from the spectrum using a basic approximation. We use this injection modulus, which we can approximate using Rayleigh-Ritz or some other numerical method.
This is in which dimension?
Sorry.
What dimension of?
Well, this is just the operator is uncertain RD, just the arbitrary dimension. Yes. So the point here is that we take this map, which is now semi-bounded below, and we can compute these matrix elements. I'll show you how to do it on the next slide, and then we just use classical techniques to approximate the injection modulus. So we pick these sample points specifically so as to produce some known error bound on the integral, and we just take a weighted mean to get an approximation to the integral, and this will give us the matrix elements, which we can then plug in here and get an approximation to the injection modulus. Then we can approximate the resolvent, and then we just basically minimize successively these approximations to get global minimizers, which is the spectrum. So now on to negative results. A quite nice result is that if we consider the set of real sparse potentials, the problem of computing the absolute continuous spectrum can't be done in one limit. So basically, we assume that such an algorithm exists, and then to each Turing machine, which can basically be thought of something that can be implemented on a computer in a sensible programming language. So this potential will encode information about the Turing machine, and then we can use the algorithm to compute information about its absolute continuous spectrum, and then we can somehow deduce whether or not it halts on all inputs, and this is known to not be done in one limit. So I can sort of sketch the idea here. Can you move this one up? So basically, we just run the Turing machine. Whenever it halts an input, we move on to the next one, and so we build up this potential where these centers. I should probably draw more distance here because the distance between them should be rapidly increasing, and if at any point we stop the machine fails to halt an input, it will just be zero beyond that point. So we'll get absolute continuous spectrum. Whereas otherwise, if the procedure can just continue, we get an increasing ladder, which will produce singular continuous spectrum. So if we could determine whether the absolute continuous spectrum was non-empty in one limit, we could somehow solve this problem in one limit, which we can't do. So we we can now think of provability. So we just have this string describing a polynomial potential. So now we're working in one dimension, and we have a ball. Can we prove? We determine whether it intersects this ball, and the answer is in general no. So the idea is basically knowing which balls intersect the spectrum, we can reconstruct the spectrum from. This should be the other way around. Sorry. If we know which balls intersect, we can construct it from below, and if we know which disjoint from it, we can construct it from above. The idea is from above is simple. We just draw a very large grid. We delete balls that disjoint. And convergence from below is basically the same idea. You add in intersecting balls, but then you have to have a procedure which eliminates balls that are not very good approximations. Which will basically be if the ball has far smaller radius and it intersects another one, we just delete the large one. So we can actually form this result if the spectral problem is not sigma 1, then there are some true intersections that we cannot verify within the axioms of ZFC. And then this is just an example. Say we have this ball, we wouldn't delete it if it was intersected by the green one, but there's a blue one, we delete the red ball to get a better approximation here. So this is just to conclude about computability. So say we have this unbounded self-adjoint spectral problem with all these operators computable. If this problem is not sigma 1, and then we can find a ball which doesn't intersect, which intersects the spectrum in the real world, yeah, this is in the relative C, and pi 1 we get similar. I should clarify this real world thing. Basically, when we encode these as Turing machines, this becomes a statement about Turing machines. So there's no sort of indeterminacy there. It is true or isn't. But ZFC can prove whether a Turing machine, say, fails to halt or it can't. So in this example, this is basically what I mean by the real world. And also, if you have a operator which describes some physical system, obviously some properties will either be true or they won't, and you can understand this in the same way. So that's most of what I had to say. So the conclusion is that not all computational problems can be solved. In fact, most can't to most people's satisfaction. It's a big problem of insisting conditions under which they can. And we've built this SCI hierarchy under which we can sort of measure the difficulty of these problems. And this is implications to provability. In fact, provability becomes basically equivalent to computability. So, are there any questions?